In this video, I want to look at the second way that we can ramp up the reactivity of the carboxylic acid derivative. So this might be an ester, it might be an amide, or even a nitrile. And the way we're going to do it is through acid catalysis. Before we begin with that, let me just remind you exactly where we've come from. So what we've been looking at up until this point is some kind of carboxylic acid derivative that is set up like this. We've got a leaving group on there, and that leaving group could be a really bad leaving group, for instance, such as an amine. This functional group would have been an amide. Or the leaving group could have been an alcohol, in which case this would have been an ester. I then showed that we can actually have a much better leaving group over there. The best, of course, is chlorine. It's a great leaving group. We make an acid chloride, which is then very reactive to nucleophiles. And we can also have an anhydride. Rather specific example, but it is also a good leaving group. In all of these cases, we've been using nucleophiles, and depending on how good this leaving group is, depends on how strong the nucleophile needs to be in order to react with a carboxylic acid derivative. And so in all these cases, we get some type of reaction happening where the process is we generate the tetrahedral intermediate, we do our shortcuts, the leaving group leaves, and we end up with our product. One of the things that we haven't looked at over here in terms of a leaving group over there is, well, what about, we've looked at esters, but what about a carboxylic acid itself? What is the problem with this reaction, and why have we not yet covered an example where we have an OH as a leaving group over there? There's a very good reason for this, an excellent reason, and that is to remind ourselves that, number one, nucleophiles are bases. They are typically good bases. And the other thing we need to remember is that carboxylic acids are acids. And so the problem with doing this type of reaction, if we're using some kind of nucleophile, whatever it might be a weak amine, it might be an alkoxide. The problem with this is that is going to take off that proton, and the bond is going to break, and we're going to end up with the carboxylate, which looks like this. And so carboxylic acids cannot react this way. It's just impossible. So what we need to do is we can't do reactions like this under conditions that would be considered basic. The way we need to do it is we need to do under acidic conditions. And this brings us back to first year chemistry, notably the Fischer esterification. So the Fischer esterification happens under acidic conditions. And let's just look at that in some more detail. What typically happens is we have some kind of alcohol, so a different alcohol from whatever the acid is over there. But the important thing here is that we have an acid catalyst. This is critical. The difference here is the acid. The base, the nucleophile that we're going to be adding on over here, the ROH over there, is a terrible nucleophile. And a carboxylic acid, there's just no ways that the lone pairs over there can react with the carbonyl and get that to occur. The biggest problem is because the lone pairs of electrons on the carboxylate can delocalize in, and that really just deactivates that position over there. However, when we add an acid, and we look at this and we think, oh, well, there's no bases present, but all lone pairs are effectively nucleophilic. What we can do is the lone pairs on the carbonyl, and it could be anywhere, it doesn't really matter, but for mechanistic purposes, it's better to just see it from the lone pair of the carbonyl. We can protonate with the acid, and what that generates for us is a reactive intermediate, which, because the oxygen is now positively charged, what we have done over there is that we have activated the carbonyl to be much more reactive to nucleophiles, even weak nucleophiles. And so in this case, our alcohol that is present, which is not a great nucleophile at all, has the ability to add to the carbonyl, and we get our tetrahedral intermediate, which we have done so often in the past. When this happens over here, we can draw our tetrahedral intermediate. Notice now, because we're under acid conditions, the difference, of course, is that we're not ending up with an O-. We're actually ending up with two OHs over there, and our R, and then this H over there. If we want to track one of those H's over there was our original acid catalyst that added. At this stage, the reaction has a number of different options that need to occur. And we must understand that what we're doing over here is actually a full equilibrium. It's an acid-base reaction, and what we've done going in the forward direction can absolutely happen in the reverse direction as well. We can protonate and we can deprotonate. This is not a very basic oxygen, so picking up the proton is not really a favored process. And so we'll lie more to this side over here. But once we protonate, this can go in. And once we get to this point, we can again also go back. All that needs to happen is this lone pair, or that lone pair over there, kicks back in and kicks out the alcohol. And we're back to square one again. However, it is possible, and again, we're doing an equilibrium, it is possible for this proton to be transferred to one of those OHs over there. They're equal to each other. It really doesn't matter which one we want to put it onto, but for the sake of just being a bit different, not putting it on there, messing with that color, I'm going to say that this H over here is going to end up over there. Now, there's a question, of course, whether this H specifically ends up on this oxygen over there, or if this H goes into the solvent and another H comes into onto this H over here. Overall, however we do the mechanism, we talk about this being a proton transfer. We've taken a proton from one place to the other. So I'm going to do it where I'm just going to show that this one leaves like that, and I'm going to show where another proton from the medium is adding to this carbon over there. And so that proton is going to leave, and I'm going to give it another H over there because it's from the medium, and we're going to end up with this intermediate over here. So not much has really happened. In some respects, it's slightly boring. All that we have done is put a proton onto a different group. A different group over there. So now this oxygen is now positively charged. It wasn't like that in the beginning. This was our original H. There's our other H over there. And this was our alcohol that added. And it could go back. The proton could transfer to this one. The proton could transfer back to that one. It doesn't really matter. These are all equilibria that are occurring in the reaction. And the next step that can happen now is that either one of these two lone pairs are going to kick in and kick this out. This has turned it into a leaving group. It's now water that can leave, pretty much like this was over here, the alcohol that could leave. This can now leave and become our leaving group. And I'm just going to choose these lone pairs over here for no particular reason. I could have used those ones, and I'm going to kick that in like that. And so what we end up over here is pretty much almost to the point of where we have our reaction product. So it looks like that. And, whoops, sorry. Silly. And of course, we've got water that has been removed. So there's our ester part over there. And this was that original H that we added right in the beginning. And that H can go. What's going to pick it up? Well, another one of those could pick up that H. Some alcohol could pick up that H randomly. It's possible. There'll be water present in this reaction because the acid is normally added from aqueous HCl. So there's a lot of things that could pick up that H. And we often don't show that, but we do need to remember that, when the H disappears or leaves, it's being picked up by something. We could, if we wanted to, there's this water that was present in the thing, and we can show that that picked it up like that. That gives us the ester. So, and this is what is known as a Fischer esterification, and we end up with a new compound that looks like that. All right. The thing with the Fischer esterification is that we have achieved something quite nice, and that is we have been able to use a carboxylic acid, which we cannot use under all the conditions that we've looked at so far. If we've got a nucleophile, we cannot use a carboxylic acid in order to generate an ester or something like that under these kind of basic conditions, it's just not going to work because the carboxylic acid is an acid, and before it's an electrophile, it's actually an acid. And once that deprotonates, the carboxylate over there is very unreactive. You've got a negative charge over here, which is delocalized. That negative charge is pushing away. Any kind of nucleophile that wants to approach in over here is going to be pushed away by that negative charge. So it's totally deactivated and a terrible, terrible electrophile. Not going to work. So the Fischer esterification, great way of making an ester under acid catalysis. Notice how we picked up the proton, and then we lost the proton. We lost this proton over here when we picked up, so that's just a proton transfer. There's no net gain, and at the end we lost the proton again. So this is only catalysis, or catalytic amounts that we need of that, and we can form the ester. The problem with this reaction, though, and why it is often not used in the lab to make esters, we actually prefer to use an acid chloride as an example, is that this is a full equilibrium. And that means that if you've got one equivalent of this and one equivalent of this, it ends up being, you basically get like a 50-50 mixture. We can make this reaction work a lot better if we can somehow take the water that's formed. We're using Le Chatelier's principle, and we can take the water off. That's usually quite difficult, mainly because we're working in an alcohol, and alcohols hold on to water very easily. So that's very difficult. The way we normally get to do this is that the ester that we're making are typically very simple esters, like a methyl ester. And so we'd be using something like methanol. And then if we're using methanol we can use in vast excess, and that pushes the reaction to completion. So that's how we would do a Fischer esterification. So what about transesterification? So remember, transesterification we looked at once in the context of taking an ester. And we used an alkoxide, so it was an ETO minus that could then react in there and it would do a displacement. There was also a one-to-one reaction because we formed methoxide on the other side, so the reaction could go backwards. But transesterification can actually work very nicely under acid conditions, acid catalyzed conditions, in exactly the same way that we would did it before, the negative, and then using an ethoxide. And also the Fischer esterifications, this whole process can also happen again. So once again, the acid can protonate this. Now protonate the ester and allow the ethanol to come in very easily. And then at some point, we're going to have to swap out between the ethyl and the methyl. And so long as you've got an excess of this, we can very easily generate the ethyl ester. So we swapped out one ester for the other. And we'd end up with methanol on the other side. And so this is again also actually a full equilibrium. It's acid catalyzed, so we haven't used any of the acid specifically in the products necessarily. We're regenerating the acid, but we are able to swap out the one for the other. We can maybe just do this in blue so we can see that over there. So transesterification is very easy to do as well. It is also an equilibrium, and once again, we need to use a lot of ethanol. What about amides? Can we make amides via this Fischer esterification process? The short answer to that is no, we can't. And the reason for this is actually quite easy to explain. So look here. If we take a carboxylic acid and we add an amine, so some sort of primary amine that we want to then combine. So we want those two things to combine, and we're going to say, oh, well, we're going to use some acid to do that. And really, the reaction that we're wanting is, the idea is to get this as a product. Let me put a prime on there. Okay. So we're wanting this to be like the nucleophile. That over here we want is the leaving group, and we'd like to see that. So it's this would be a condensation reaction. So we're giving off water at the end, one of those hydrogens and the OH over there. So that's what we want to be able to do, but this doesn't work. It's not going to work at all. And the reason it doesn't work is because of the chemistry that's involved and what we need to happen. So remember, what we need to happen is that the proton, which is in catalytic amounts, needs to protonate the oxygen over here to activate this. Now, if that happened, that would be great. The nucleophile would definitely be able to get in there. The problem, though, is that in these two components that we have over here, The amine that's here, this is a weak base. Amines are weak bases. And so in the presence of the acid is absolutely going to react with the amine and form the ammonium, which is going to look like that. And once that happens, we've taken away the very thing that we need for this reaction to occur. We needed that lone pair. The lone pair of the nitrogen needed to react over there, and we've just knocked it out with the very thing that we need for this reaction to occur. So amides are absolutely impossible to make via this type of reaction. However, amides can be hydrolyzed in the other way. We can take the amide product and under acid conditions, in the presence of water, we can absolutely go to the starting materials that we have over there. That works. However, for hydrolysis of amides, it's not the best way of doing it. Using base, which we've discussed already, is far better. But it is possible to do it. Again, we would need to use acid and water, and this is going to need a lot of heat and really cooking it up in order to get it to react. The last functional group that we need to look at, just to remind ourselves of this using under acid conditions, is the carboxylic acid derivative, which doesn't look like a carboxylic acid derivative, and that is the nitrile. And nitriles can also be hydrolyzed under basic conditions as well as the acid conditions in exactly the same way that we generate an amide can be hydrolyzed. We just need to use a lot of heat, some acid and some water, and what that will do is it'll hydrolyze a nitrile into a carboxylic acid, and then the leaving group will be ammonia, so the ammonium at least. So this nitrogen was the leaving group over there, and it gets fully protonated by all the acid that's adding and the water that you're getting from there. And all these waters over here are from, these oxygens are all from water. So we've had to add two equivalents of water. You can go and look up those mechanisms, and you perhaps a good idea is actually for you to try and work it out yourself first. Think about how in both of these cases over here, going from an amide to the carboxylic acid and the amine, how would you do each of those steps that are involved in that process? Follow the esterification, the Fischer esterification as a starting point. And likewise here, remember this has got a lone pair. We're going to protonate there first, activate, and then start bringing water in. And try and do that mechanism, and then go and check up in your textbook to see if you are correct.